Hello everybody, in this lecture we will be solving 1985 IMO problem number 4. Here is a view of this problem. Given a set M of 1985 distinct positive integers, none of which has a prime divisor greater than 23, prove that M contains a subset of 4 elements whose product is the fourth power of an integer. Okay, so let's begin by first listing the prime numbers less than 23. So we would have 2, 3, 5, 7, 11, 13, 17, 19, and 23. These are all the primes less than, so these are all primes less than or equal to 23. In fact, I will just represent them as p sub 1, p sub 2, p sub 3, and so on. P sub 4, p sub 5, 6, 7, 8, and 9. So we have in total 9 prime numbers. And now it's clear that for an arbitrary integer, let's call little m, in the set M, we would have the following representation, the prime factorization I should call, p sub 1 raised to the power k sub 1 times p sub 2 raised to the power k sub 2, and so on, up to p sub 9 raised to the power k sub 9, where k sub I are positive integers, right? So with the possibility of 0 as well. Now, the critical part. So, when will it be that when we multiply 4 of them, we'll get a fourth power of an integer, right? Let's begin with a simpler question. What shall happen so that when we multiply 2 of these elements, and we get a perfect square, we get a second power of an integer? And of course, yes, you're right. So, each of these powers of the product should be an even number, right? So what it means is all the powers of every single one of these 9 primes should agree with each other. So if you have two numbers, let's say m and n, when you multiply them, it means you add their exponents. Let me give you an example, for instance. P sub 1, L sub 1, P sub 2, L sub 2, and so on. P sub 9, L sub 9. So if I have to multiply them, m times n, what I'll get is p sub 1, k sub 1 plus L sub 1 times p sub 2, k sub 2 plus L sub 2, and so on, up to p sub 9, k sub 9 plus L sub 9. Now, for this expression to be a perfect square like x squared, what we need is each one of these exponents must be even. What does that mean? So k plus 1 plus L plus 1, and all of them, k plus 9 plus L plus 9, should all be even. But what that, and all of them, so right? So what that means is that their powers, the parity of their powers should agree, right? So if k1 is odd, L1 has to be odd as well. If k2 is odd, L2 has to be odd, and so on. If k1 is even, L1 has to be even as well. If k2 is odd, L2 is odd. If k2 is even, L2 is even. So what is necessary for when we multiply two numbers from this set M is that all the powers agree with each other. That gives us an idea on how we can proceed. In fact, I will exactly pursue this route. Let's first represent, or maybe I should say assign to each m in M a vector, a 9 tuple, let's say x sub m, as x sub 1, right, so x sub 2, and so on, up to x sub 9, such that, that's the key definition, x sub I is equal to 0 if k sub I is even, and x sub I is equal to 1 if k sub I is odd. So in this 9 tuple, each number, which is a binary number here, by the way, right, zeros or ones, each one depend on what k1, k2 is, right? So for instance, for the number m, if k1 is even, we'll have x1 0. If k1 is odd, x1 will be 1, and so on. We'll check k2 depending on k2 is odd or even, right? So we'll have our vector here. But then we have a great idea coming. Notice that before I mentioned this idea, because each of these entries are binary, in total we have 2 choices for this one, 2 choices for each and every single one of these 9 entries. So in total, the space of all these vectors can contain at most 2 times 2 times 2. So basically 2 to the 9 vectors, which happens to be 512. In total, we have 512 different type of vectors, or different type of numbers, we should say, right? So therefore, what's interesting is I can apply pigeonhole principle now in the following sense. So if I pick by picking, let's pick say 1 more than this. By picking 2 to the 9 plus 1, which is 512 plus 1, 513 integers in M, it is guaranteed that at least 2 of them will have the same representation in terms of these x vectors, right? Then there exists at least 2, say a sub I, b sub I in M, such that their vector representations agree with each other, implying that that's the important conclusion, implying that their product as well will become a perfect square. So let's say C sub let's call it A sub 1 and B sub 1 for the time being. Okay, so A sub 1, B sub 1, A sub 1, B sub 1. As a result, there exists a number C, an integer C sub 1, such that the product A sub 1 times B sub 1 is equal to C sub 1 squared. So meaning that A sub 1 times B sub 1 is a perfect square. Now what I will do next is I will simply remove A sub 1, B sub 1 from our list. So remove A sub 1 and B sub 1, both of them, from M. So we would get, in that case, to obtain a new set, let's call it M sub prime, which doesn't have the elements AI and BI, right? So remove those from the set. And this set, well, M sub prime, oops. Okay, so you guys get the idea. So this is our set M prime, such that M prime would have 1985 minus 2, 1983 elements in it. And guess what? I have enough elements to apply pigeonhole principle again, because in order to execute pigeonhole principle, I should have 513 integers at least, and I have enough. So I can apply pigeonhole principle again, actually, and continue applying it, right? Continue as long as we have at least 513 elements remaining, right? So each time we apply pigeonhole principle, we will remove 2 elements. We'll find 2 elements with the same representation. Their product will be a perfect square, and we remove them afterwards. But how often can we do it? Can we do it? We claim that we can do this repetition. We can repeat at least, what I need is to repeat this at least 2 to the 9 plus 1 times. if I repeat this 2 to the 9 plus 1 times, I should have enough elements, right? So let's see if I have enough elements. So if I repeat this scheme 2 to the 9 plus 1 times, in each time I will remove two numbers, a sub I and b sub I. As a result, 2 times 2 to the 9 plus 1 elements will be removed, which is 2 times 513, which is 1026 elements removed. And in order for me to remove the very last pair, I should have at least 513 remaining in the set, which obviously I have, because 1985, the original number, minus this number 1026, is still giving me a number which is more than what I need, right? So it would be like 959. So this is more than the 513 needed to execute the pigeonhole argument here. So as a result, now I have the following. So I have removed a list of a sub 1, b sub 1, a sub 2, b sub 2, up to a sub 513, b sub 513, such that each one is a perfect square. So this one, c sub 513, is a perfect square, right? Is equal to a perfect square when you multiply them. That's what I mean. So a1, b1, a2, b2, and so on. A 513 times b 513 is equal to a perfect square. But then I can apply pigeonhole principle one last time, right? Okay, here we go. So let's first organize things. So let's figure out what c sub 1 is. C sub 1 is a sub 1, b sub 1. Obviously, this is decidedly a positive integer. In fact, it's a positive integer with prime factors of p sub 1 and p sub 9. The only prime factors of c sub 1, of course, will be these numbers, because each and every single one of these a sub 1 and b sub 1 had prime factors like this. And when you take the square root, of course, you will have the same type of prime factors. And you can repeat this for all the c sub I, c sub 2, c sub 3, and so on. So what will happen is you will have a list of c sub 1, c sub 2, c sub 513, in total 2 to the 9 plus 1 elements, each with the following prime factors. As a result, there will exist at least 2 of them. By pigeonhole principle, one more time, there exist at least two of these, such that, let's call these c sub I and c sub j, such that c sub I times c sub j is equal to, say, d squared. But that's exactly answered where d is a positive integer, for d is a positive integer. But this is exactly what we needed, because now we can replace these expressions with their definitions here. In fact, let's just take the square of both sides. Squaring, we get c sub I squared times c sub j squared is equal to d to the power 4, which is just a sub I, b sub I, and c sub j, which is a sub j, b sub j. So therefore, we have found 4 numbers, all a sub I, b sub I, a sub j, b sub j, all in the set M, such that their product is a perfect 4th power. And that solves the problem. Hope you enjoyed the solution, and looking forward to see you guys in our next lecture.